Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now, back to the show. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. My guest today is Matthew A. McLain, Ph.D. He's the interim dean of the School of Science, Math, Technology, and he's also the health chair of the Department of Biological and Physical Sciences. He's an associate professor of biology and geology. This is all at the Master's University. So we're going to talk about vertebrate paleontology, dinosaurs, etc. So welcome, Matthew. Thank you.
Hey, thanks for having me.
If you would, tell me a bit about your background and how you got to study the areas that you're currently studying.
Yeah, sure. So I basically just get to be a grown child in some ways, which I guess technically everyone who's an adult is a grown child. But, I get to keep a lot of the childhood stuff with me because as a kid, you love dinosaurs and animals and things, and I get to still work with that today. So I decided when you do paleontology, you can go either a biology or a geology route. And so I did geology for my bachelor's and then went on to work on my Ph.D. in earth sciences. And my project was paleontology focused, working on a dinosaur bone bed in Wyoming. And it's fun and exciting stuff.
So how long have you been working? So you're doing actual field archaeology where you go out and you dig and you collect samples directly from the field?
Yeah. So I do go out and digs. There is a distinction between archaeology and paleontology. So archaeology, you're working on like human artifacts and human civilization, that kind of stuff. Whereas paleontology, you're doing extinct animals and plants and fossils of those. And so, we'll go out and I'll dig out in Wyoming with a team out there in June, typically. And then I get to do some other stuff around, because I'm in Southern California. And so there's lots of fun stuff even right around here.
You should joke and say, do you have like a Berea tar pit in your backyard or something?
Actually, the provost of our school used to have fossils in his backyard. He moved. But when he was there, I took students up there and we found, first it was just shells and stuff. We found shark teeth and even bones of like giant manatees and whales and stuff. It was pretty cool.
Oh, wow. So, in archaeology and in paleontology, I would think paleontologists are in the field a lot more. I don't know. But what percentage of professionals in both fields have field experience versus being in the lab all the time?
I would say, if you go through and get a degree in one of those fields, typically you've been in the field for some part of time in your work. Not everyone, but a good chunk of them. But a lot of that actual research doesn't happen in the field. That's kind of the conception we have of watching Indiana Jones or Jurassic Park or whatever. Like, a lot of what you do is visiting museum collections, it's writing, it's, working to put your ideas together. So, you'll spend some time in the field, typically in your break times, like summer, things like that. But a lot of it is actually happening in the museum and in the office.
Oh, okay. What are some of the most critical things that allow you to do your work? I would say radiocarbon dating is probably absolutely critical, but that seems to be, at least according to some scientists, like fraught with a lot of controversy and problems. What are the maybe that, and I don't know what else. What are the critical things that allow you to do your work, to be able to assess what you see?
Yeah. So we typically, in paleontology, we actually don't use a lot of the radiometric dating methods. So radiocarbon dating, you can only use on stuff that is more recent. So like you're thinking about trying to think best way to phrase it, but conventionally people would say like 40,000 years to the present you can use carbon dating. And even when you're getting back in that older time, it gets a little screwy. And so when you're working with stuff that's supposedly older than that, then you can't directly date the bones, because you'd have to use other methods like uranium or argon or things like that are not typically found in the bones in large quantities. And so you're actually using, kind of regardless of what you think about issues related to age of the earth or anything like that, you get to use a lot of the same methodology, which is what we call relative dating methods. So it's doing stuff like, saying, okay, this rock is underneath this other rock. So, the one on the bottom has to have been there first, and the one on top was there second, or you're using the fossil record to help you correlate things. So you're looking at, the particular types of pollen or clams or things that you find in your site and comparing it to other places around the world and trying to come up with, okay, when exactly were these layers laid down? And then we do a lot of fun science in our field called Taphonomy. And what you do there is you are basically doing ancient CSI work. So it's, forensic science, but applied to the deep past. You're trying to figure out what this animal, what happened to it after it died, what happened after it was buried. And there's all kinds of a myriad of things that can happen there. And so that's a really fun side of it as well.
Yeah. Tell me about taphonomy. What's an example of what you've done? That sounds really interesting.
Yeah. So like one thing that I focused on as part of my PhD, we were looking at tooth marks. So, if an animal bites another animal, whether it's dead or not when it bit it, they can sometimes leave marks on the bones if they bit deep enough and things like that. And so, you can study those bite marks to learn things about what bit the animal, what kind of a bite was it doing when it did it. You might be able to learn things about, okay, was it feeding on it? Was this some kind of fighting behavior? Things like that. So, we had a fun example of a Tyrannosaurus bone, like a young Tyrannosaurus bone that has bite marks on it. And we were actually able to figure out the bite marks came from another T-Rex, and the kinds of bites they were, where they were located in the body, all those kinds of things. We were able to say, yeah, this looks like a feeding trace. This thing was eating something else. And so you can actually start to kind of reconstruct some of those stories, which is really cool.
I'm picturing dinosaurs like giant dogs, laying there with a bone and just crunching it. We have all kinds of marks on the bone.
Yeah. Well, and you can do modern experiments with this stuff, right? So you can look at, there were some scientists that took a goat carcass and gave it to a Komodo dragon in a zoo. And then they retrieved the bones after it was done with it, and they could see, okay, when it turns its head, it leaves this kind of bite. And when it, clamps down on it, it leaves this kind of bite, and those kinds of things.
Oh, nice. That's really cool. Yeah. Question before we go into this more. When I was growing up, I learned all the dinosaur names because I love them,
Yeah.
Now it seems like all the names have changed. I don't get it. Like I learned about brontosaurus and Triceratops, the Stegosaurus, and now all the names are different. Like what happened?
Yeah. So there's a few things going on there. One is just discovery, right? We find new things all the time. And so there's a lot more species we know about now than we used to know. But part of it is also the rules of biological nomenclature. So, for instance, when back in the 1800s, there were these big rushes to find dinosaurs to try and fill museums with cool looking skeletons and stuff. And so you had these people competing to try and name new species. And as a result, you got some stuff that was poorly named. They found like a random tailbone and they're like, okay, this is a new dinosaur. And it's like, are you really sure about that? This could look like a tailbone and another one that you named just from a skull. And so sometimes the names that we got originally, we got used to, it turns out, actually, this is really this other creature. And so the name kind of gets sunk underneath another one. And so the classic example of this kind of thing is brontosaurus. So back in the 1800s, they found several of these long-necked dinosaurs out in the American West. And so they named a few of them, things like Brachiosaurus, like you see in Jurassic Park, Apatosaurus, Brontosaurus, Camarasaurus. And pretty quickly, some people realized Brontosaurus and Apatosaurus are really similar dinosaurs. And so some paleontologists were saying, actually, Brontosaurus excelsus really should be called Apatosaurus excelsus. It should be considered a species of the genus Apatosaurus. But because the Brontosaurus skeleton they put up in museum, everybody already seen this in the early 1900s and everything. People were super excited about it. And so it just got carried away with it. And that became the name for that animal. even though in science they were saying, yeah, don't use that name. The public was familiar with it. Well, the fun part of this story is that in 2015, it kind of flipped around because some scientists did some more work on it. And they said, you know what, actually, brontosaurus is different from apatosaurus. And so they brought the name back again. And it's been really fun since then because this is like the classic thing. When I was a kid, and if you knew a lot about dinosaurs, you'd like, tell adults like, oh, brontosaurus isn't real, like, haha, I know things that you don't know. And now I get to turn it back on kids and like, actually, brontosaurus is real. Take that, So you have these funny things like that with the way we name things in science.
Okay, yeah, because I was wondering, because like I said, none of the names seem to be the same, so I thought, this is weird. But okay, that explains it. What are you able to tell from the taphonomy? So I know what the intent is to figure out how the animal lived, how it died, etc. But what actually has been discovered that maybe is not commonplace knowledge? Were you able to discern, dinosaur behavior, or what have people been able to figure out through taphonomy?
Yeah, so it's actually useful in a lot of ways that you wouldn't necessarily immediately expect. So one of the big ways is it gives you timetables for how long it takes before things become fossils or before they become buried or things like that. So, back in the day, you read these books, fossils or dinosaurs or stuff from the 1900s, 1960s, 1970s. And it's all this like, oh, the animal died. It kind of fell in a river. It slowly got buried with sediment. And, and then it, like somehow you get a perfect skeleton of that. Well, as people started doing taphonomy work, they realized, no, that's not how this works at all. Like if an animal just dies out in the wilderness, it's typically gone, like pretty fast. You've got all these decomposers and things that destroy it. And so if you're finding like a pristine skeleton laid out, that's telling you, whoa, this thing must have had some special conditions to preserve it. It had to be buried rapidly. It had to be protected from bacteria and from decay and all those kinds of things. And so there's some fun examples, like my Ph.D. advisor and some of his colleagues did work in Peru. And they were working on fossil whales they found out there. And these whales would just be beautifully laid out, the entire skeleton, everything articulated together. And sometimes the whales still had their baleen near their mouths. Well, when they've done studies on modern whales, they discovered baleen falls out of the mouth in like days, typically a week after death, maybe 8 days. And so okay, this thing had to be buried within 7 or 8 days. And a whale's a big animal. So you can have a lot of sediment coming on top of that thing to bury it and protect it from scavengers and just decay processes in general.
Yeah, well, what happened? A dinosaur fell down dead. Supposedly was laying there for thousands, hundreds of thousands, millions of years and was slowly covered. Like, what, if you went to uncover it later, what would you see? Would there even be a fossil versus a rapid
nothing left? I mean, so there's been some good studies. One of the experts in this field is Anna Berensmeyer, and she works with Smithsonian, and she went out to the African Serengeti and just observed, what happens when an elephant dies, what happens when, these different animals, their bones, they lay out there. And she started categorizing it and saying, within a year, this much weathering happens. And within, 2 years, this kind of damage happens. And they're not around very long. And especially if you're in a wet, like a humid climate, things are around even less because you've just got so much more activity happening to destroy those things. And so, I'll tell you, the site I worked at for my PhD, we found a weird combination of things. We'd find bones that were like pristinely preserved, like just beautiful things you'd see in a museum. And then you'd find other things that were like junk. We just called bone gravel. And we're figuring, why on earth are you getting these completely different signatures happening? And so, we suggested maybe this is what we call a mixed assemblage. So some things are being buried very soon after death, whereas other things might have been buried a while ago and then they got like maybe a flood came through and picked up the bones again and reburied them. And so a way you can test this is what's called, you can use rare earth elements. You can look at the bones and do geochemistry on them. And when you do this, if you get all the same signature in the bones you look at, they're all buried in the same place. But if instead you're getting wildly different chemical signatures, then you can say like, oh, this one was buried, this time, this one was buried at a different time or a different place, and they've been moved and reaccumulated somewhere else. And sure enough, we had our geochemist was working on it. He found, yep, these are wildly different signatures. These things have different origins. And so I kind of compare it to and explain it to people. It's kind of like a freeway. When you think about like in California or a place like that, where you've got like all these roads that come together to make like a really big freeway. You have cars coming from all kinds of different places. And you imagine like if you just suddenly stopped, took a picture right there at when all these ramps merged together to get on the freeway, you'd have cars from all kinds of different places, as opposed to if you take a picture from a road before you enter that, when it's just from one direction, you might have people all from the same kind of place, And so when we do physical and chemical taphonomy and all this stuff, it can really help us give us a window into things that we didn't even realize going on.
Yeah, no, that's really cool. So in the fields you're in, I guess there's slow burial people, there's fast burial people, or what is the split called? And what's the reasoning from the slow burial people?
Sure. So, a lot of that just comes with the baggage of history, right? When you had back in the 1800s, when they switched over with Charles Lyell and Charles Darwin, all these guys that were pushing uniformitarian processes and time, just this idea of like things always happen slow. They always just happen in normal ways. Just ignore catastrophes. Don't think about them. It was kind of just ingrained in people to automatically think, oh, I see a rock layer. It's really old. It accumulates very slowly. And it's been with the advent of taphonomy and some of these other fields that people have started saying, ooh, wait a minute, that's not actually the case. And so what I would say is it's more like they don't necessarily fall into camps anymore. It's kind of just more like, do you have the philosophical baggage that you've brought with you, or have you been kind of looking at it with new eyes as you've done these other fields of study? And so the really cool example of this, the one that gets everybody excited, is that now they're finding actual preserved soft tissue and even like proteins and bits of DNA and stuff in fossils, even things like dinosaurs. And so this is a really wild one, because not only do you have to have rapid burial, but even with all the perfect conditions, we don't know how to make proteins and DNA and stuff like that last for, 70 million years or 100 million years. These things can only last for, even the best conditions, you might be able to stretch it to 1 million, you might be able to stretch it to a few 100,000. But this is just completely blowing everybody's mind that people are finding this kind of stuff.
Yeah, that's crazy. Very interesting. What are some of the, so when you interact with other scientists in your field, someone is in the, slow burial camp, I guess I'll call it. Are you able to work with them, or they're like, oh, you're an idiot, you know nothing like that? Are people still cooperating, or is this really driving a wedge between scientists and the fields you're in?
I would say that one's not so much of a big deal. People, there's always those difficult people, when you're working with other scientists. I think you run into more problems when you're willing to question things like, whether we've got the age of things correctly, just overall, or whether you might be suspect of particular like evolutionary hypotheses or things like that. That's kind of where you run into more difficult situations where people might not be willing to work with you, or, so some of those bigger paradigm worldview kind of issues. But when it comes to taphonomy, it's kind of one of those things where everybody's like, well, yeah, the more we look at it, the more it looks like pretty much every one of these, you have to have, if you've got a good skeleton laid out, that's an exceptional circumstance. There's really very few people that are disagreeing with that now.
Oh, that's really cool. So how rapid were some of the burials you've seen? How fast must it have been in order to preserve the animal in the way it was preserved?
Yeah. So, when you look at like a site, like I said, if you've got, a full skeleton laid out, it's articulated, it's all put together and stuff, you can think about how you see a dead animal on the side of the road, right? The first few days, yeah, like it's still together and everything. And a lot of the times it's going to take, a week or two before you start really seeing the bones fall apart. If you don't have scavenging, obviously, if you have scavenging, that's going to go a lot faster. And so it's not like every fossil we find, we can say immediately, oh, that's exactly how long it was. But you can get these big picture kind of thing. Sometimes you get a really clear picture, so I'll give you one example. There's a scientist named John Whitmore who did work on fossil fish in the Green River Formation in Wyoming. And it turns out that he did some really gross experiments. Basically, he had to like put rotting fish in tanks and let them sit there for weeks. And it was, bad smells and stuff. But the fish, they have very predictable ways they decay. And so like if you find a nice, and this site out in Wyoming is famous for really beautiful fish. So you open it up, flip open a rock layer, there's a beautiful fish laid out there. Hey, that thing had to be buried very rapidly. You're talking about days. Sometimes you'll find a fish that is like a J shape. And it turns out that as they begin to decay, the gases build up in the swim bladder. And so it kind of makes the belly float higher, and it gives them this J looking shape. And you can find fossils like that. And so, okay, that one was sitting out long enough for this process to take place. So now you're looking at, a few more days. But sometimes you will find a fish that has actually exploded. Okay. So basically what happened is the gases built up so much in the swim bladder that it burst. And it turns out some fish, their swim bladder is connected to their ears. And so when their swim bladder exploded, their head would also explode. And so if you look in the Green River Formation, you can also find fish that have exploded. And so that's telling you something about the water depth as well as the amount of time that's taken place. So those ones decayed even longer. And so you can start putting that all together and you can say, okay, this one was a few days, this one was maybe a few weeks, but you're not finding anything that's like a year or, 5 years even. Like, these are tiny bones in these animals. They're going to be destroyed very, very rapidly. And so when you're finding sites that have good fossils like that, it's rare to find anything that looks like it was sitting out for, longer than a year, I'd even say.
Oh, wow. Are there any fossil deposits where there's enough of them over enough of an area of land where you can reconstruct, the conditions that led to all their demise? Some were, looks like, oh, okay, over here, they were very quickly, over here it was slower, over here, blah, 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 et cetera. Has anyone been able to do that?
There's some places you can do stuff like that. So, where I work, and we're in Cretaceous layers, so it's like dinosaur stuff in Wyoming. There's one particular bone bed layer that is full of pretty much every bone has the same kind of preservation. It's all kind of one type of dinosaur in there called a brontosaurus. The bones are jumbled up. They're not connected anymore. And so we're able to say, okay, based on the features we see in the geology here, the sediments and how the bones are arranged and stuff, this is pretty clearly some kind of like a big mud flow type thing, something like that moved these bones. And so we can recreate a scenario of these animals were alive, they died, they had time to articulate, but not enough time for the bones to get really damaged. And then, mud picked it up, moved it, deposited it. Well, just across the valley, there's like a little ravine. You go up in the next hill is where I was digging before when I talked about we had the mixture of really good bones and really, really bad bones. And so there we're saying, hey, this is more complicated. And so, these layers may only be within, a few meters to tens of meters of each other in elevation. And yet we get a very different story in each one of those. And so we can start to begin to kind of do that in the whole area, which is what we're trying to do.
Okay. I've heard from various people that, they say, oh, it's an asteroid strike that wiped out the dinosaurs. And then obviously the people that are creationists, say it was a worldwide flood. Can the two reconcile? Was part of the, would a meteorite impact be part of the conditions that created the flood or helped it or hastened it or made it worse or more extensive? Or are the two seemingly totally separate events or, one is not even existent?
Yeah. So, I don't think you're going to get the secular side of it necessarily to acknowledge a global flood. They might, one day acknowledge that the earth was flooded by water at one point, but they're not necessarily going to agree with all the elements of the story in the Bible, right? But on the flip side, there is really good evidence for an asteroid impact in the Yucatan Peninsula in Mexico at that spot where we stopped finding dinosaur fossils. And so the creationists would say that, it does look like it's there. And so this would be something happening during the global flood, near the end of it. And, you'd also have tons of volcanic and earthquake activity, of plate tectonics happening. And so, you could definitely have an asteroid impact occurring during a global flood. It could leave evidence that it was there. It could help bury things. If there were things alive in that area, it could kill them. I don't think I don't think that you have to get rid of the one to hold on to the other. Could have both happening simultaneously.
So is it enough? So when you look at the totality of all the fossils that you've looked at, all the evidence, everything, what does it say to you? Does it say that, global flood was responsible for laying down a lot of the fossils that we see? Or was it a combination, maybe again, of asteroid strike, global flood, and other stuff? What do you see?
Yeah, I'm a creationist. I think there was a global flood, and I think you do see a lot of good evidence for that as you look at the rock layers. That creatures you've got marine fossils on the continents, and you've got all this kind of stuff happening. And that being said, we've never observed a global flood, right? So I talk to people and they think it's just like, oh, if you had like a little mound of sand in the bathtub and you just filled it up with water, it's just going to make a big mess, and they don't expect that there be any order to the fossil record or different events happening. But that's not a good model, right? We're talking about the entire Earth. We're talking about for a period of like a year, this is happening. And if you imagine there's also plate tectonics happening with earthquakes and volcanoes, you're going to have a very dynamic setting where different things are happening in different parts of the Earth. And so, yeah, you might be having an asteroid hit in Mexico, and you might be having, volcanoes erupting in India at the same time, which is even what they think is happening in the conventional model. And that could all be happening during a global flood. And so I think that the reason so many people are so hesitant immediately in invoking and thinking about a global flood is they have this very small perspective of what a global flood would do or could happen during a global flood, instead of realizing that, hey, this is a really big, this isn't like a single event. Like we're thinking about something that stretches over a long, relatively long period of time, a year, months, those kinds of things. And so different processes are happening during this. it's not just one big process, but it's many, many different kinds of processes and events as a part of one big event.
And some of the fossils, I'm picturing them in my mind. Some of them seem to be completely intact skeletons. I noticed the heads seem to be bent back.
Yeah.
It's weird. They die in like a weird position, some of the fossils. Why is that? Has anyone observed why they have certain shapes, like that particular bent back shape?
Yeah, that's a great question. That's something that we find in many complete dinosaur skeletons, and it's actually got a name. It's the apostolic death posture. And the old story for this back in the day is they said, oh, they're drying out. And so the thinking was when the animal died, it fell over, and as the carcass was kind of desiccating, tendons and ligaments and stuff would pull tight on the back of the neck and pull the head back toward the back, and then pull the tail also up toward the back. Problem is, no one actually did any experiments on this. They just said it. Like, oh, that's probably what happened. And everyone just got like, okay. It wasn't until later people started trying to do experiments and they realized we can't replicate this. Like when you're having these things dry out, it's not happening. And so there's a group from Brigham Young University, published this as an abstract at a conference. They haven't officially published the paper yet, to my knowledge, but they took chicken carcasses and they started putting them in these different environments. They put them in a drying environment. They put them under water. So they put them under salt water. They put them under fresh water. And what they reported was that nothing happened in the drying environment. Didn't look like it. But in fresh water, like almost instantly, you put the chicken carcass in there and it would bend back. The neck would bend back toward the back. And so that's really interesting. And that's particularly fascinating because many of these, some of these skeletons that we find this posture in, things like Archaeopteryx or Microraptor or things like that, they are supposed to be buried in lagoons or lakes or things. And so that's possible. But some of these skeletons are coming from areas that people typically thought of were like arid, desert type environments. So like some of the stuff in Mongolia. And, we've been saying, if we think of this global flood, there probably aren't any arid environments happening at this time. Probably are no deserts at this time, right? It's underwater. And so this seems to actually match better with that idea. But once again, this is an area where we need more experimentation happening. I'd love to see people jump into that more.
I watched like CSI on TV, and I remember they talked about, when people die in water, their flesh becomes something like adipocere or something, some weird term. And I guess it's probably disgusting how it, puffs up and comes off bones. And so is there any evidence, any of these fossils, I know the flesh and it's not the bone, but any that would have died in a column of water instead of being buried with sediment, like they'd be sitting at the bottom of some body of water decaying that way? What would that look like?
Yeah, so you do see some evidence that some of these carcasses were in water for a while. So for instance, there's a whole group of dinosaurs called the ankylosaurs, and these are the ones that have all the armor on their backs, the tanks walking around. Yeah. So interestingly, almost every time these guys are found fossilized upside down. And that would make sense if you sink in water, right? You've got all this heavy armor on one side of you. You're gonna tip upside down. We've got some evidence of shark bites on some of our dinosaur fossils. So these things were obviously out in the water for a while. But a lot of times, once again, you think about a global flood happening, you are going to have massive sedimentation events happening underwater too. So even if you sweep away a dinosaur, dead or alive, out into the water, you've got sediment that's moving as well. And can bury it as part of that process, just like you would in I think about like a river flood or something like that, or a tsunami. And so you could have both things happening, and we do see both things. We see some things that show very rapid burial. Some animals, there's some examples in Mongolia where it looks like they're actually buried in life position, where an animal's sitting on top of its nest of eggs, or it's just sitting there and it's just buried, on like a statue. And then you find other ones, like I said, where they look like they've been moved, they've been transported out to sea, and they were falling apart in the ocean and sunk. You find all kinds of different examples like that.
That's really interesting. Have you been able, or other scientists been able to learn various things about the nature of the global flood?
Yeah.
How fast it came, where it started, where it went to, et cetera.
Yeah, that's great question. So I'm focusing on the fossil side of things, so I don't get into a lot of that, but I do read it, and I talk to those guys who work on those things. And so one of the big things in the last 30 or so years that really come out is recognition that the continents moving must have been part of the flood, and that there's been this model developed called catastrophic plate tectonics. And it was developed by a team of creationist scientists led by a guy named John Baumgartner, who's a geophysicist. And they did work kind of demonstrating, okay, what would happen if you had particular scenario, and could you get plates moving faster, and could this be a driving force for the flood? And it looks like, yeah, actually you could get something like that. And it deals with something called runaway subduction. So when you've got a oceanic plate we talk about plate tectonics, the oceanic crust, when it's sinking underneath another crust, going down into the Earth's mantle, you can get this scenario happen where if you have the right initial conditions, you can create this runaway effect where it starts heating up and that causes it to move faster. It heats up again and causes it to move faster. And so kind of like you think about like a nuclear meltdown and that runaway idea. And when that happens, you can move the continents much faster than the way they're moving today. And it ends up allowing for some really particular effects of the flood to occur, for the water to get onto the continents as the continents kind of get dragged down at their margins. So you're creating new ocean crust during this. It's higher than normal, hotter than normal, causes the oceans to be higher than normal. And so you can get some really fun things that happen through this modeling that's like, yeah, you would actually generate a global flood if you had this scenario. And so where we pull in the fossil side of things is we can look at, okay, can we use the fossils to help us find where the flood started and where it ended in the record? And so that's what I do, more of that kind of thing, where we're looking at, okay, we would expect there to be kind of like a discontinuity, right, between the types of fossils you're finding from the pre-flood world versus the things you find after the flood. And so we're using fossils to help us locate that. So one project I was just involved with recently, we were looking at the continents of South America and India. And so both of those continents, like I talked about continents are moving, both of them collide with other continents. So South America is an island for quite a while, and then it bumps into North America. And in the conventional model, people talk about the millions of years and things, they have an event they call the Great American Biotic Interchange. And that's where animals from South America go into North America, animals from North America go into South America. And so that's why we have like armadillos and possums and stuff in North America. And it's why South America has llamas and jaguars and stuff. They swamped. And so we're like, cool, we want to find out, did this really happen? And depending on where you put that boundary between the flood and the after the flood stuff, that will either make sense or it won't make sense, right? So for instance, if you think that's happening during the flood, that those continents hit each other, well, that's really weird. Like, why are you only finding armadillos in one place in the world? And then suddenly you're finding them in another place in the world during the flood. And then after the flood, they go and live in those exact same places, right? Like, so what you'd have to have, Australia is the classic example of this. If this stuff is happening during the flood, and you've got kangaroos living in Australia, you find their fossils there today. Well, those kangaroos must have gotten on Noah's Ark, flood happens, Ark lands, and then those kangaroos go back to where their ancestors lived. Like, that's a really weird idea, Instead, it makes more sense that all of those fossils are after the flood. So South America and North America colliding with each other is an after the flood event. Animals then are moving into those places. We're actually watching that change happen in over time, which is what we would expect to see. But
so if the flood happened, all animal life would have been wiped out,
right?
Except for stuff in the sea. So land animals, wouldn't they, if they would have come off the ark, which would have happened, I guess, around Turkey, Saudi Arabia, everything would have dispersed from there. So was there like Gondwana land or like a massive single continent, people think after the flood, or how did animal dispersion happen?
Yeah. So, if we're right about where we put this boundary, the continents are near their present positions. There's a little bit of difference at the end of the flood. So for instance, South America is technically an island at that point, as is India, and Australia is closer to Antarctica, as is South America, than they are to where they are today. And so, you've already got Europe, Asia, Africa together still. So animals can move into those places, no problem. How do you get to somewhere like the Americas or Australia, right? Well, if you're a flying or swimming animal, no problem. Obviously, you can make your way over to those places. But there's a really cool thing. We talk about this in the science of biogeography, which is why we have the animals where we do on the Earth today. There's a thing called rafting. And so basically what happens is during a big storm, like a hurricane, you can get big mats of vegetation that come off of a continent and will float out into the ocean. And sometimes there are animals on these things. And these animals can ride these like rafts and end up places. So this was observed in the 90s. There was a hurricane that came through the Caribbean, broke off a big raft of vegetation. You've got iguanas on it. Those iguanas got transported from one Caribbean island to another one, got off there, and started a population there. And so you imagine at the end of the flood, you've got tons of debris in the ocean, plenty of opportunity for rafting to occur. And so that's how you could transport some of those animals immediately after the flood. And we'd predict that over time, those rafts are going to be destroyed, right? Your world's going to kind of calm down from a global flood over time. And so we'd expect less and less of that going on as you make your way up the rock record. And that's what you see. Cenozoic, you see initially tons of animals pop up in South America. Here we are. And then not very much going on for a very long time. And then all of a sudden, when South America and North America collide completely after the flood, when you have formed the Isthmus of Panama, then suddenly they all switch places again, right? So that's what we might expect versus if it were actually millions of years of time, those rafts are just happening on random occurrences of storms. You'd expect it to be kind of more regular, like every few million years, another group of animals gets transported over, instead of there being these distinct bursts of activity.
So what do fossils look like pre-flood versus during the flood versus post-flood? Are there any discernible differences?
Yeah, so the actual fossils themselves, you're probably not going to notice much of a difference. And there's different types of fossilization too. So, something might be preserved by a particular mineral versus another mineral, or something might be original material versus it's all been dissolved away and replaced with rock. There's different ways that can happen. But what we'd be looking for, fossils that are forming in the pre-flood world, we'd expect there's probably not as much activity, but we would expect that there should be some stuff, like shell debris, things that you'd expect to find in our world today. In the flood, you could expect anything that's alive could potentially be buried. But in the post-flood world, what we would expect to see is actual environments changing over time, right? We'd expect to see the Earth recovering and seeing geological and paleontological evidence of that. And so what you see in the layers we call the Cenozoic, you can find initially lots of evidence of a really warm tropical world. Then you can see it kind of cooling down to grasslands and those expanding over continents. And then you can see eventually an ice age occurring and then humans migrating around as well. And so that's kind of what we'd expect to see in the aftermath of a global flood is that kind of drying out, cooling out process. And of course, the spreading out of humans occurring after the spreading out of animals.
Is there a total absence of dinosaurs after the flood?
Yeah, so we don't have any dinosaur fossils. If you're excluding birds, that's a whole discussion, whether birds are dinosaurs or not. But things we typically think of as dinosaurs, you don't find their fossils after the flood, except in some cases in some places like New Mexico, where there's probably what we call reworking, where a bone was buried by the flood, but then, a river came through and eroded it out and it got reburied again kind of thing. But what that's telling us is dinosaurs never reestablished big populations after the flood. And they're not the only animals like that. There's tons of animals from the fossil record that are dinosaurs but are extinct today that it looks like they just didn't cope with the new world. And that's what I think a lot of people miss when they start thinking about the topic of a global flood is it's completely destroying the world of before. Your continents are different places. You've got different rivers, different mountains. Everything is different and different ecosystems. And so you have
climate's different.
Yeah, climate is different, right? So you've got whole ecosystems that no longer exist. So if you're an animal that's on the ark and you're used to having this particular forest of, sphenophyte and lycopsid trees, and you get off the ark and that's gone, too bad. You're not going to win. You're going to die. And so when we think about animals coming off the ark, it's a free for all. It's go out and colonize. And if you're really good at colonizing this world, awesome. You're going to do great. If you're not so great at it, you're going to struggle and you're potentially going to go extinct. And so a great example is amphibians. So when you look at fossil amphibians and the layers we think are laid down by the flood, there's dozens of different types of amphibians. There's things like the size of school buses. There's things with boomerangs for heads. There's things with fins on their back. There's crazy stuff. Today, we have 3 types of amphibians. We have salamanders, frogs, and caecilians. And frogs, there are more species of frogs than there are mammals, which is crazy, right? So what are we seeing there? We're seeing that when the amphibians got off the ark, frogs are this is our place. And they excel. They've got the body type for it. They fit this new world really well. Whereas these other amphibian groups, they just can't cope and they don't make it.
Do you see a continuity though, pre-flood and post-flood, where most of the animals still around? Or are they all totally different? Or is there a small subset? What does it look like if you look at the totality of all the
So there are a lot of animals that cross over, so you get crocodilians and turtles and a lot of lizards and snakes where you can find the same families before and afterward. The unique things really deal with things that go extinct, so things like dinosaurs and pterosaurs and stuff. But you've also got animals that we first find fossils of in the post-flood world. And so that's things like a lot of our mammals. There are mammals in the dinosaur layers, but they tend to be different. And birds, same kind of thing, where there are some bird groups that we still have today buried with dinosaurs, but most of them are different bird groups. And so the question is, where are all of our fossils of mammals and birds and humans that we're familiar with from layers laid down by the flood? And what we tend to think is that particular community wasn't preserved by the flood. It was decimated. It was just completely destroyed. And there are different reasons to explain that, how that might be, or it could be we just haven't found the fossils yet. That's possible. But it looks like they were a minor component to the fauna. The world of pre-flood world, I think, was dominated by reptiles, dinosaurs, things like that. That was much more most of the earth. Whereas our Earth today is very mammal and bird dominated when you think of the land masses.
Yeah, why do you think that is? It seems like before the flood, a lot of the animals around were pretty big. Maybe I'm mistaken, I don't know. And then after the flood, in general, they were a lot smaller. Of course, you have woolly mammoths and things like that. But it just seems like, for the most part, most of the creatures are a lot more than they used to be before the flood. Like, why do you think that is?
So I think some of that is just our biases and unfamiliarity as we look at it. And I talk to people all the time. I always have students asking me these questions, or when I'm talking to people in churches, why were animals so big back then? Well, not all of them were. Salamanders, we got some big salamanders today. They got some big ones then. They got small ones then too. It's certain groups of animals. We do see that, so we had dinosaurs, we had giant flying animals, but probably our biggest marine animal of all time is alive today, right? It's blue whales. So not everything follows that pattern. And actually during the post-flood time, we have this really cool trend of a lot of mammal groups getting bigger over time. So like horses and elephants and groups like that, they actually start off very small and they get larger. They diversify in the post-flood world. And then right around the time of the Ice Age, right after the Ice Age, you have what we call the Pleistocene megafauna extinction, where a lot of our big animals just go extinct. So when you look at, like, if you go to the La Brea tar pits, for instance, in California, you find fossils of saber-toothed cats and dire wolves and mammoths and mastodons and stuff, and ground sloths. Everyone's excited about those. You also find tons of bones of turkeys and red-tailed hawks and chipmunks and skunks, all the same kinds of animals we have today in California. So identical species. Yeah, we just don't think about them. But the big ones all died. And so you kind of a collapse that happened.
Yeah, what I realized is my perception is that the only thing that was around before the flood were dinosaurs. Big, everything was big.
Right.
I think that's the impression that everyone gets, is like everything was huge. And then after the asteroid, the flood, etc., everything was small.
Yeah.
But it's not true at all.
No. So you get big things both sides, you get small things both sides, But the thing is, when you go to a museum, you don't want to see tiny stuff, right? That's big dinosaurs. And so I think that's why we get attached to those, because they're more exciting. But there's tons of little tiny animals running around in Mesozoic and Paleozoic layers. They're all over the place.
Okay. Very interesting. What are some of the new things that you're working on now? Now that you understand this, you've been doing this for years, et cetera. What are some of the current questions you're trying to answer?
Yeah, I'm always diving into more research projects than I should probably. I love it. It's fun, so it's hard to pick out things. But I would say there definitely are some big unanswered questions we have in paleontology, especially as we think about like a creationist form paleontology with a global flood and things. So one of them is why, if you did have a global flood, why is it creating so much order? Why are things, you never find... So, for instance, you don't find a human fossil with a T-Rex. But you also don't find T-Rex fossils ever buried with stegosaurs, even though they're both in the United States, sometimes in the same state, and so there are these very particular layers where you only find particular types of animals. And so that's one of the big questions we want to start working on, is figuring out, okay, what is the reason for this? How do these things get separated? How is the flood preserving ecosystems during this giant watery catastrophe? And it could be we're wrong. Maybe those layers aren't deposited by the flood. Maybe we got our boundaries wrong. And so that's, these kind of things we always evaluate and reevaluate. And that's how science works, right? Is put out hypotheses, you test them, and certain things we've proposed look good and it looks like they're fitting with the data well. Other things we proposed, we're like, I don't really know what to do with that. And so I think sometimes the way creationists get portrayed by non-creationists is like, oh, well, they don't do science, or, they can't test their ideas, and because they can't falsify their ideas because they just believe what the Bible says. And it's like, well, yeah, I do believe that the Bible says there's a global flood, but on the science side of things, there's a ton of things to explore there, right? Why did dinosaurs die out immediately after the flood if they were on the ark? How do we explain like different processes that are at work there? And so a lot of what I get to do here at Master is really cool. I get to do research projects with students. And so some of the research projects we do are things we could get published in a secular journal, things that are not explicitly creationist. If any scientist could do it, so we'll find a cool fossil and we'll describe it. And so I'm going to have some students helping me out with some of those kinds of things, or visiting museum collections and looking at bones of different types of reptiles and trying to understand how do they live, how are they related to each other. But then on the flip side, I've got other students who want to do things that are explicitly creationist, where they're helping build the flood model, they're helping us understand what are the different created kinds of organisms and how do we define those boundaries. And so I end up being involved in lots of different kinds of projects like that.
Yeah, no, that's really cool. How do you feel like scientists of faith differ from ones that are secular? Yeah, I don't know if you can say they're all more open-minded or not. I mean, they seem to be attacked more than secular scientists, but what do you see as the difference or differences?
I think on a certain level, I mean, certainly they're all human. If you're being a good scientist, you are seeking to be objective. You're seeking to work with data and interpret things faithfully. And you are trying to do, good experimental work. You want other scientists to look in and see what you're doing. In terms of differences, I think one of the big ones is, I guess the way to say it is we're playing with a fuller toolkit. So, when you talk to a scientist who's a committed naturalist or materialist, someone who would say, like Carl Sagan, the cosmos is all there ever was, all there will be. They're ignoring the possibility of supernatural. They're ignoring the possibility of a God. They're automatically throwing out those tools. They're saying, well, I don't want to believe this is the case. And so they're approaching trying to solve problems without that information. So one of the cool things as a creationist scientist is I have to understand non-creationist thinking just as well as I understand creationist stuff. And that gives me a wider variety of hypotheses to draw from, a wider variety of tools to use. I can approach a problem in that way. So that's a little bit different. I would say the biggest difference, honestly, is just the deeper understanding of recognizing that if there is a God, and he created this stuff, his design is everywhere and it's giving glory to him. And when I go to, secular conferences and I hear them talk about, look how amazingly designed this creature was by evolution, or how amazingly designed it was by nature, and it's like, you're seeing this amazing handiwork, this amazing, you're agreeing with me. It's fantastic. You're just as amazed about it as me, but then you're attributing it to like a random process, as opposed to saying, this is really well designed. That should be attributed to an intelligence. And so you're misattributing who actually made the thing.
Right. Yeah. Okay. Well, what's the best way for people to literally just start seeing all the material you have, experiencing it if they want to go deeper? Like, what's the first thing they could do, or the first place they could go to see, the papers and all the things that you've worked on over the years?
Sure. I'd recommend like our first place to go to. It's a thing called the Center for Thinking Biblically. So it's thinkbiblically.org. So our university puts we have our professors create specific kind of short courses and put them on there free to view. And so I've got one on dinosaurs. I've got one on Earth history. So like just kind of giving people basic overviews of those things. When it comes to like actual more technical work, so looking at different journals and things. I don't know if you ever do like show notes. I mean, I could give you some stuff there, but regardless.
Yeah, that would be great.
Okay. Yeah. I mean, people can always look me up on, ResearchGate, or just go to the Masters University webpage, and a lot of that stuff is listed on there as well.
Okay. Very good. Well, Matt, it's been a great call. I really appreciate you being here, and thank you so much for coming.
Yeah, thank you. It's been really good.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.